What's up, YouTube? Okay, today we're going to look at adding and subtracting radical expressions. Doesn't that sound like fun? Okay, let's review the parts of a radical expression. When you have this, the radical, the number in here is called the index. The number or expression that's underneath the radical is called the radicand. And of course, this thing right here is the radical itself. Okay, now if we if the index and the radicand, R-A-D-I-C-A, are the same, then you can combine them. You can add them. So, in other words, if we have 5 times the square root of 3 plus 4 times the square root of 3, the indexes are both 2. We just don't write it because it's assumed to be a 2. So are these like terms? Yes. So this is going to be equal to 5 plus 4 times the square root of 3, which of course is 9 times the square root of 3. And again, in order to be able to add or subtract, the radicand and the index have to be the same. Okay? So if we have 2 times the square root of 7 minus 6 times the square root of 7, are these like terms? Yes. Indexes are the same. The radicands are the same. So it's nothing more than 2 minus 6 square root 7, which is, what is that, negative 4 square root 7. Okay? Now this is more like what you're going to see on the final exam and in your algebra class, your college algebra class. If you have 4 times the square root of 18 plus 5 times the square root of 2. Now, can we factor the 18 into 2 numbers, or 3 numbers, I guess, into 2 numbers where one of them is a perfect square? Yes. 18 is 2 times 9. 9 is a perfect square. So we can say that this is 4 times the square root of 9 times 2, or 2 times 9, whatever, plus 5 times the square root of 2. Now look, this is 4 times this. So the square root of 9 we know is 3. So it's 3 times 4, right? Square root 2 plus 5 times the square root of 2. Now this is 3 times 4 is 12. Square root 2 plus 5 square root 2. Are these like terms? Yes. The indexes are the same and the radicands are the same. So this is, what is it, 17 square root 2. Okay, the one thing to remember here is when you take this out of the radical, the 9, this is going to be, the square root of 9 is 3. It's going to be 3 times 4, like we have here. Okay? Now, these problems are going to get a little bit longer, but they really don't get any more difficult. Take your drink of your Diet Coke. Okay, what are the factors of 300 where one of them is a perfect square? This is 100 times 3 plus, and the square root of 27 is 9 times 3, right? Right. Now the square root of 100 is 10 square root 3 plus the square root of 9 is 3 square root 3, right? So this equals 10 plus 3 is 13 square root of 3, right? Right. Okay. How about this? Get this if you're so smart. The fourth root of 32 plus the plus 3 times the fourth root of 2. Now, what is the fourth root of 32? We can factor that into the fourth root of 16 times 2 plus 3 times the fourth root of 2. Can we take the fourth root of 2? No. Can we take the fourth root of 16? Yes. It's 2 times 2 times 2 times 2. So that is 2 times the square root of, excuse me, 2 times the fourth root of 2 plus 3 times the fourth root of 2. Are these like terms? Yes. So this is 5 times the fourth root of 2. Okay. Okay. Let's see. And how about this one? This is about as difficult as these get, and it's really not very difficult. If we have, it's just a little bit longer. Minus the square root of 32 plus 2 times the square root of 50. Now, what are the factors of 18 where one of them is a perfect square? It would be 6 times the square root of 9 times 2 minus 16 times 2 plus 2 times the square root of 25 times 2. Okay, so this is going to equal square root of 9 is 3. 3 times, let me do it like this, minus square root of 16, excuse me, is 4 square root 2 plus the square root of 25 is 5, so it's 5 times 2, right? Square root 2. Okay, let's clean this up. 18 square root 2 minus 4 square root 2 plus 10 square root 2. Okay, 3 times 6, 18. 4 is just there by itself, and 5 times 2 is 10. Now, are these like terms? Yes. Square root 2, square root 2, square root 2. So we can add these or combine these. 18 minus 4 is, what is that, 14? And 14 plus 10 is 24 square root 2. I'm sorry I'm going so fast, but we've got a lot of stuff to cover. Okay. And what about this one? 5 square root 54 minus 2 square root 24 minus 2 square root 96. Now, if these are not familiar to you, look on that sheet that I sent you that showed the cubes and the squares of all the numbers. So this is 5 times the square root of 9 times 6, 9 is a perfect square, minus 2 times the square root of 4 times 6, minus 2 times the square root of 16 times 6. Okay. The square root of 9 is 3. 3 times 5 is 15, square root of 6. Minus square root of 4 is 2. 2 times 2 is 4, square root of 6. Square root of 16 is 4. 4 times negative 2 is negative 8, square root of 6. So are these like terms? You betcha. 15 minus 4 is 11. 11 minus 8 is, I think, 3. 3 square root 6, I think. Okay. I'll get this one if you're so. This is really about as difficult as these get. When they put these godless letters and stuff in here. So the square root of 18k minus the square root of 72k. Okay. Now, the factors of 18 where 1 is a perfect square is the square root of 9 times 2, and don't forget the k, minus the square root of, what is that, 36 times 2, k. Okay. Square root of 9 is 3. 3 times the square root of 2k. The k will not come out of the radical because we haven't taken the square root of it. Minus the square root of 36 is 6. Square root of 2k. Are these like terms? Yes. So we have 3 minus 6 is negative 3 times the square root of 2k. Okay. Now, got that. Now, we're going to go on to multiplying and dividing radical, R-A-D-I-C, radical expressions, S-S-I. Okay, before we were adding and subtracting. Now we're going to be multiplying and dividing. The same stupid stuff we've been going over since day 1 in this class. The only thing is we've got radicals in here. Godless radicals. Okay, square root of 5, open, 2 plus the square root of 6, closed. Okay, now remember that the square root of 2 times the square root of 5 is the square root of 10, right? We multiply the radicands. Okay, now here we have, excuse me, here we have the distributive property, right? So we're going to distribute the square root of 5 times 2, and then that one. So this one is 2 times the square root of 5, right? That times that, plus square root of 5 times the square root of 6 is the square root of 30. Are these like terms? No. So that's all we can do. Okay? Get this if you're so smart. For open square root of 12 minus the square root of 27. First of all, can we factor this stuff in here where one of the factors is a perfect square? Yes. Square root of 12 is the square root of 4 times 3 minus the square root of What's the 9 times 3? Okay. So this equals 4 times 2 times the square root of 3, right? The square root of 4 is 2. It comes out of the radical. Minus the square root of 9 is 3. 3 times the square root of 3. Right? Right. So now we multiply 4 times everything inside of here. So that's going to be equal to 8 times the square root of 3 minus, what is that, 12? 12 times the square root of 3. Are these like terms? Yes. 8 minus 12 is, what is it, 4? Negative 4 square root 3. We said algebra is not fun. That's good stuff, huh? Yeah. Okay. Get this if you're so smart. Square root of 6, open parenthesis, 3 plus the square root of 2. Okay, again, distributed property. So it's going to be the square root of 6 times 3 is 3 times the square root of 6. Right? You cannot multiply something under the radical, the radicand, times a whole number, other than just like this. Plus, now the square root of 6 times the square root of 2 is the square root of, what is that, 12? Square root of 6, square root of 2. Can we factor the 12, can we factor the 6 into a factor that's a perfect square? No. Excuse me. 3 times the square root of 6 plus 4 times the square root of 3. Right? Right. So this equals 3 square root 6 plus 2 square root 3. Is there anything we can do here? Can we combine these things? No. Can we factor the 6? No. That's all we can do. Can't do no more. Okay. Where are we? Square root of 10. Open. 5 minus the square root of 3. Close. Well, I hope y'all appreciate this. I'm doing this on my Saturday. Yeah, like I've got anything better to do. Boy, that's a good Diet Coke. Distributed property. We have 5 square root 10 minus. Now remember, when we have a square root, both of them are, the indexes are the same. They're both 2's. So we can multiply these two. Minus, was that 30? The square root of 30. 10 times 3. Can we factor the 5 into something that's a perfect square? No. Can we factor the 30 into something that's a perfect square? No. So that's all we can do, and we cannot combine those. Okay. And what about this? 5 open square root 72 minus the square root of 8. This is equal to, again, distributive property. We have 5 times the square root of, well, let's go ahead and factor the 72. 72 is 36 times 2 minus 5 times, what is that, 4 times 2? I just bit my lip. You know, I've had these teeth, it seems like, for about 150 years. I think I'd learn how to chew by now. Oh, goodness, stupid boy. Okay. Square root of 36 is 6. 6 times 5 is 30, square root 2. Square root of 4 is 2. 2 times negative 5 is negative 10, square root 2. Are these like terms? Yes. 30 minus 10 is 20, I think. 20, square root 2. Anything else we can do? No. Okay, let's review what is a conjugate. Remember, I hate to say I told you so, but I told you so. We're going to use conjugates quite a bit. So if you have 3x plus 2 times 3x minus 2, okay, the numbers are the same. The only difference is one's a positive and one's a negative. Now what's that going to do? It's going to eliminate the linear term, the middle term. So first of all, we take 3x times everything over here, and that gives us 9x squared minus 6x. Is that right? Yeah. Now we do the same thing with the 2. 2 times 3x is plus 6x. 2 times negative 2 is negative 4. See, the linear terms, the middle terms get eliminated. So that gives us 9x squared minus 4. If you'll notice, this is a perfect square. The difference of squares, and again, the difference of squares, you can factor that back into that. Difference of squares is a conjugate. Or we just went frontwards and backwards. Now we're going to use this because what's going to happen is we want to eliminate this middle term here, the linear term. We're going to want to eliminate that. And the way we do that is with a conjugate. Excuse me. Now, if we have this, the square root of 3 minus 5, and my lip's bleeding. I hope y'all appreciate this. You know, I'm going to all this trouble. I got injured on the job. Ooh, I wonder if I can get workman's comp. Okay. Now, what is this? See, the numbers are the same. Square root of 3, square root of 3, 5 and 5. But one's a negative and one's a positive. So what's going to happen there? The linear terms will be eliminated. So and remember, should have done this at the beginning. The square root of any number times itself. What happens? When you multiply the square root of numbers that are exactly the same, the radical just goes away. What this actually equals is the square root of x squared, which is x. And again, what happens if you multiply two square roots that are exactly the same? The radical goes away. If you have square root of x times the square root of any number times itself, it's just the number. Okay, so square root of 3 times the square root of 3, what happens? The excuse me, the radical goes away. So we have 3. Actually, this is square root of 9. And what's the square root of 9? 3. Square root of 3 times 5 is 5. Wait a minute. Plus 5 times the square root of 3. Now we do this one. Minus 5 square root 3 minus 25. 5 times the square root of 3 minus 5 times the square root of 3, those get eliminated because they're the same number, just subtracted from each other. So we get 3 minus 25 is negative 22. Now look, what you can do if you recognize the fact that these are conjugates, really all you have to do is multiply this number times this number and that one times that one. Because remember, the linear terms get eliminated. So if you have a conjugate, if you see that it's a conjugate, just multiply the first numbers and the last numbers. Okay? Okay. And let's do another one. The square root of 7 plus the square root of 14 times square root of 7 minus the square root of 14. What do we have here? Look, the numbers are the same. Square root of 7, square root of 7, square root 14, square root 14. But one's positive and one's negative, so what is this? A conjugate. So the square root of 7, now we're just going to do the first numbers and the last numbers because we know that the linear term will be eliminated. Square root 7 times square root 7. Remember, the numbers are the same, so the radical just goes away. So this is going to be 7 minus, again, square root 14, square root 14. The radical goes away. Negative 7. 7 minus 14 is negative 7. Okay. Get this if you're so smart. First, let's drink. Square root of 5 plus 2 closed, all squared. Is this a conjugate? No. What does this mean? It means square root 5. When it's squared, it means this number in the parentheses times itself twice. Square root 5 plus 2. Okay? How we do distributive property? Square root 5 times square root 5 is the square root of 25, which is 5, right? Or the same numbers under the radical just goes away. Now we do square root 5 times 2. Same thing here. 2 times the square root of 5 is 2 square root 5, and 2 times 2 is 4. Do we have any like terms here? Yes. 5 and 4. 2 times the square root of 5 and 2 times the square root of 5. So we have, 4 times the square root of 5, right? 2 and 2 is 4. 2 square roots of 5 and 2 square roots of 5. Plus 5 and 4 is Nina Ross. Rides a big white Baldwin horse. Where are we here? Yeah. Okay? Okay. Rational numbers. Now, what is a rational and what is an irrational number? A rational number can be written as a fraction. Like 1 over 3, 5 over 1, 2 over 3. All these things, these are all rational numbers. How about pi? Pi is an irrational number because it cannot be written as a fraction. Square root of 2, square root of 5, square root of 7, those are all irrational numbers because they cannot be written as a fraction. Okay, now we cannot have irrational numbers like this, these are irrational. We cannot have irrational numbers, R-A-T-I-O-N. Cannot have irrational numbers in the denominator of a fraction. Okay? Now, the way we get rid of those is called rationalizing the denominator. Sounds like a disease, doesn't it? I got me a bad case of that irrational number in my denominator. Okay, so what if we have this? 5 over the square root of 2. This is an irrational number, and we cannot have irrational numbers in our denominators. Whew. I'm telling you, it sounds like something you need a shot of penicillin for. Okay, so how do we get rid of it? Get that if you're so smart. We're going to multiply by 1. Now remember, when you multiply by 1, it does not change anything. It just changes the look of it. So what can we do to get rid of this irrational number? We're going to multiply by the square root of 2 over the square root of 2. Square root of 2 divided by itself is 1, right? So we're not changing the value of this any. We're just changing how it looks. Now we do that. When we multiply fractions, it's straight across. Don't have to find a common denominator or any of that misery. So this is 5 times the square root of 2, right? Right. Square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is 2. Remember, when you multiply the square root of any number times itself, the radical goes away. This is called rationalizing, R-A-T-I-O-N-A-Z. Rationalizing the denominator. And remember, the denominator is the one on the bottom. Okay? We cannot, this is an irrational number, we cannot have that. Somebody figured that out a long time ago. Wouldn't you love to find them and strangle them? We have 11 divided by square root of 3. Square root of 3 is an irrational number. So how are we going to get rid of it? We're going to rationalize it. So we're going to multiply by square root of 3 over the square root of 3. Any number divided by itself is 1. So really we're just multiplying times 1, but it just looks different. So 11 times the square root of 3 is 11 square root 3 over square root of 3 times the square root of 3 is the square root of 9. Square root of 9 is 3. Or you can say, if you multiply the square root of any number times itself, the radical goes away. Now, can we divide 11 by 3? No, not evenly. So we leave it like that. Okay? So you get this one. 6 times the square root of 3 over the square root of 2. Can we take the square root of 2? No, it's an irrational number. So we're going to multiply by square root 2 over square root 2. So this equals 6 times the square root of 6, right? 3 times 2. When they're under the radical like that, you can multiply the 2. Square root 2 times square root 2 is square root 4. And the square root of 4 is 2. Now, can we divide 6 by 2? Yeah. Can we divide square root of 6 by 2? No. Only this one. 6 divided by 2 is 3 square root 6. Okay? 6 divided by 2 is 3. And when we do that, then this one goes away. That is 3. Okay. 5 square root 2 over square root of 5. Again, we have an irrational number in the denominator. I'm telling you, that sounds like a disease to me. So we're going to multiply. We're going to rationalize the denominator by multiplying square root 5 over the square root of 5. So this is 5 times the square root of 10. Okay, square root 2 times square root 5 is square root 10 over 5. Those can be eliminated. So can we factor the square root of 10 into something that's a perfect square? No. Let's drink. Okay, negative 6 divided by 12. Now we can factor 12 into one number that's a perfect square. It's going to be 4 times 3. So we have negative 6 over 2 times the square root of 3. Square root of 4 is 2 times the square root of 3. Okay, so we can take that out. Makes that a 3. This is 3 over square root 3. Right? Right. So now we, what do you call it? Oh yeah, rationalizing the denominator. So we're going to multiply by the square root of 3 over the square root of 3, which is 3 times, an awful lot of 3's in here. 3 times the square root of 3 over, remember when you multiply the square root of any number times itself, the radical goes away. Oh, this is negative, I'm sorry, that's negative 3. Okay, sorry, I'll do better. No, I'm not going to do better. Okay, negative 3 divided by 3 is negative 1, or just negative, times, those eliminate, times the square root of 3. Right? Right. Okay. That's all of that misery. Now, what if we have a binomial in our denominator? That really sounds something. It really sounds like something bad. My irrational number, binomial. Okay, what if we have this? 3 over 1 plus the square root of 2. Now, how are we going to get rid of this? Where if we just multiply by 1 plus the square root of 2, we're going to get numbers. We're not going to eliminate the radical. So how are we going to get rid of this? We're going to multiply by, its conjugate, 1 minus the square root of 2. 1 minus the square root of 2. Okay? Because if you multiply by 1 plus the square root of 2, you're going to get a square root. You're going to get an irrational number in the denominator again, and that you have to eliminate that somehow. And how do you eliminate the linear term? By multiplying by its conjugate. Again, I hate to tell you I told you so, but I told you we were going to use these godless conjugates somehow. Okay, so now we multiply the 3 times everything over here. Remember, this is the distributive property. So it's going to be 3 minus 3 square root 2, right? Everybody see that? Over. Now again, we have the conjugate here, so really all we have to do is multiply the first numbers and the last numbers, and that's all, because we know that multiplying by the conjugate, the linear term gets eliminated. Okay, so that's going to be 1 minus square root 2 times square root 2 is 2, right? We just eliminated that thing. So we have 3 minus the square root of 2 over -1. Now, if it was up to me, I'd say this was okay like this. But they want you to divide. Yeah, divide everything by -1. So you're going to get -3, excuse me, plus the square root of 2. Right? We're dividing everything by -1, which the only thing that happens there is the signs get changed. Who said this one? This is good stuff. Minus the square root of 3. So how are we going to, yes. What are we going to do here? Going to multiply by the conjugate. Times 4 plus the square root of 3. 4 plus the square root of 3. Remember, this is actually 1. Any number divided by itself is 1. So we're not changing the value of this, just changing the look. Okay, so we do distributive property here. So this is going to be 20 plus 5 square root 3. I just got a message that this meeting is going to end in 5 minutes. So if it craps out here, that's what that is. And again, when we multiply by the conjugate, we're just going to multiply by first numbers and last numbers. 4 times 4 is 16 minus 3. Negative square root 3 times square root of 3 is -3. So this equals 20 plus 5 square root 3 over 13. Is there anything else we can do here? Can we reduce any of these fractions here? No. So that's all there is to it. What could be more fun? Okay. Look, they get a little bit longer than this, but they really don't get any more difficult. You know what to do. Distributive property, conjugate, all that misery, and then combine like terms. Okay. That's all there is to it. Y'all take care. Bye-bye. Hope you have a good weekend. How about those Astros, huh? Yeah. All right, be good. Bye-bye. Bye, Bonds.